These are the solutions to the Chapter 3 test review. Problem 1. Solve x squared minus 6x plus 5 equals 0 by graphing. So when we graph, we need to first plot the vertex. So a equals 1, b equals negative 6, and c equals 5. To find the vertex, we're going to use x equals negative b over 2a. So substitute negative 6 over 2 times 1. 6 divided by 2 is 3. The x value of the vertex is 3. Substitute that value into the original equation. Y equals 3 to the second power minus 6 times 3 plus 5. Y equals 9 minus 18 plus 5. Y equals negative 9 plus 5. Y equals negative 4. So the vertex is at 3, negative 4. That's a point in the fourth quadrant. Now, since the a value is 1, the size of this parabola is the same as its parent function. So I'm going to use the pattern 1, 1, 2, 4, 3, 9 to plot the rest of the parabola points. It's symmetric, so I'll do it on the other side as well. Try to do this as best as you can. Since we're looking or wanted to solve this by graphing, we are looking for the x-intercepts. Where does a parabola cross the x-axis, or the roots? So the parabola crosses the x-axis at the values 1 and 5. These are the solutions. Problem 2. Solve the quadratic by factoring. A is 1, b is negative 4, c is negative 12. I'm going to use the giant X just as a technique to organize my information. On the top, a times c, that's negative 12. On the bottom, it's b, which is negative 4. So I'm thinking of two numbers that multiply to be negative 12 and add up to be negative 4. That's negative 6 and 2. So I'm going to rewrite in factored form the quadratic. So x minus 6 times the quantity x plus 2 equals 0. I'm going to use the zero product property. X minus 6 equals 0. X plus 2 equals 0. And solve each individual equation. So one of the solutions is 6. And the other solution is negative 2. On problem 3, we're solving this quadratic by factoring. A is equal to 1, b is equal to negative 4, c is equal to positive 4. I'm going to use the giant X to organize my information. A times c is 4, b is negative 4. Two numbers that multiply to be positive 4 add up to be negative 4, negative 2 and negative 2. So I'm going to write the quadratic in factored form. The quantity x minus 2 times x minus 2 equals 0. I'm going to separate, and as I'm thinking of separating, I'm noticing that I'm going to get the same equation twice, so I'm just going to write it one time. The x value is 2. There is only one solution, and that solution is x equals 2. Problem 4. Solve the quadratic by using square roots. When I use square roots on a quadratic like this, I'm going to get the x squared term, the quadratic term, by itself. So I'm going to subtract 27 to each side. That's 3x squared equals negative 27. I'm then going to divide by 3. Negative 27 divided by 3 is negative 9. And now I can use the square root, because the square root will cancel out the squared unit. Don't forget your plus or minus. So x equals plus or minus. The square root of 9 is 3. The square root of negative 9 is 3i. So two imaginary answers. X equals plus or minus 3i. Number 5. Solve the quadratic by using square roots. I'm going to subtract 64 to each side. 4x squared equals negative 64. Divide each side by 4. X squared equals negative 16. Take the square root of each side. So x is equal to plus or minus, square root of 16 is 4, the square root of negative 16 is 4i. So two solutions, x equals positive 4i, x equals negative 4i. Problem 6. Which method would you use to solve this quadratic? We're going to circle one of these, and then we're going to solve the equation using that actual technique. So I have three choices. Now, when I do completing the square, I always have to take the middle term, divide it by 2, and square it. Well, if I take the middle term, my middle term is 7, divided by 2, that's going to give me 3.5. So I begin working with decimals, and I kind of don't want to do that. I don't want to work with decimals, so I'm not going to use completing the square. Well, what about square roots? Well, if I'm going to use square roots, I still have to use completing the square. So again, I don't want to do completing the square because I would start working with decimals. Let me try to factor. And if factoring doesn't work, then I'll go to square roots. So if I'm going to factor, a is equal to 1, b is equal to 7, c is equal to negative 18. So two numbers that multiply to be negative 18 and add up to be positive 7. That's negative 2 and positive 9. So actually, this one seems to be working out nicely. Negative 2 times 9 is negative 18. Negative 2 plus 9 is positive 7. So I am definitely going to use factoring then. So I'm going to rewrite my quadratic in factored form. X minus 2 times the quantity x plus 9 equals 0. I am now going to use the zero product property. X minus 2 equals 0. X plus 9 equals 0. So one of my solutions is positive 2. And the other solution is going to be negative 9. Problem 7. We're adding these complex numbers and we want to write our answer in standard form. In standard form, a complex number is a plus bi, where the real part is in the front and the imaginary part is at the end. So these two complex numbers are each written in standard form. 3 is the real part, 2i is the imaginary part. This is a complex number here. 5 is the real part, 7i is the imaginary part. So since I'm adding these complex numbers, I can just drop the parentheses and I'm going to combine like terms. So I'm going to combine the real parts, that's 8. I'm going to combine the imaginary parts, that's positive 9i. So the answer is 8 plus 9i. Problem 8. In this problem, we're subtracting two complex numbers. When we subtract, we need to distribute the negative sign on the second complex number before we can drop the parentheses. So 6 plus 5i minus 4 minus 3i. Now we can combine like terms. So I'm going to combine the real parts. 6 minus 4 is 2. I'm going to combine the imaginary parts. Positive 5i minus 3i is positive 2i. So the answer written in standard form is 2 plus 2i. Number 9. Now we're multiplying complex numbers. We're going to write our answer in standard form. When we multiply, we distribute or use FOIL, repeated multiplication. So I'm going to multiply the first terms. 3 times 2 is 6. The outer terms, that's negative 9i. The inner terms, multiply 5i times 2 is positive 10i. And the last terms, that's going to be negative 15i squared. Now in the middle, I can combine like terms. I can combine negative 9i plus 10i. That's a positive 1i. And every time you come across an I to the second power, we're going to change that to a negative 1. I to the second power is negative 1. 6 plus I plus 15. Negative 15 times 1 is positive 15. We're going to combine like terms now. 6 plus 15, those are real. That's 21 plus 1i. That's my imaginary part. Number 10. Again, we're going to multiply. We're going to use repeated distribution. Repeated multiplication. 5 times 2 is 10. 5 times 4i is positive 20i. Negative 6i times 2, negative 12i. Negative 6i times 4i, that's negative 24i squared. Combine like terms. 10 plus 8i, 20i minus 12i is 8i. Take away 24 times negative 1. Again, I to the second power is negative 1, so we're going to change that. There was an I squared here, so I replaced it. I substituted negative 1. 10 plus 8i plus 24. Combine like terms. That's 34 plus 8i. Number 11. Write the quadratic equation in vertex form and do it by completing the square. Okay, if we're going to put this in standard form, it's currently, right now, it's in standard form. So we need to get it in the form y equals a times x minus h squared plus k. And we're going to do this by completing the square. So first, we're going to subtract 100 to each side. So y minus 100 equals x squared plus 18x. Now I'm going to complete the square, so I'm going to go off to the side over here and find the c value, b divided by 2 squared. That's 18 divided by 2 squared. That's 9 squared, which is 81. So we're going to add 81 to each side of the equation. Y minus 19 equals, okay, x squared plus 18x plus 81. That's a perfect square trinomial. I'm going to factor that perfect square trinomial, and I'm going to do that on the side over here. Two numbers that multiply to be 81 add up to 18, 9 and 9. So this perfect square trinomial factors out to x plus 9 squared. And last thing that I need to do is bring the negative 19 back over here. So I'm going to add 19 to each side. So y equals the quantity x plus 9 squared plus 19. So the equation in vertex form, y equals the quantity x plus 9 squared plus 19. And the vertex, we can identify it from this equation, is negative 9, 19. Let's do that again on number 12. Okay, so let's get x squared plus bx on one side, so two terms, these terms here. Let's move the 26 over to the other side. Y plus 26 equals x squared minus 2x. There's a number that we're going to add to each side of the equation. That number we're going to obtain by doing b divided by 2 squared, where b is negative 2. Negative 2 divided by 2 is negative 1, and negative 1 to the second power is 1. So we're going to add 1 to each side of the equation. So y plus 27 equals, this is now a perfect square trinomial. X squared minus 2x plus 1 is a perfect square trinomial that I'm going to factor. Two numbers that multiply to be positive 1 add up to be negative 2, negative 1, and negative 1. So x squared minus 2x plus 1 factors to x minus 1 squared. I'm going to move the 27 back to the right-hand side by subtracting it. So y equals the quantity x minus 1 squared, take away 27. That is the equation in vertex form. The vertex of this parabola is 1, negative 27. Number 13. Find the value of x. We're given a rectangle, we're given the dimensions of the length and the side, and we're given what the total area of the rectangle is. Well, the area formula for a rectangle is length times width. I'm going to substitute. The area is 24, the length x plus 2, and the width 2x minus 9. So I'm going to use distribution. I'm going to multiply x plus 2 times 2x minus 9. That's 2x squared minus 9x plus 4x minus 18. Combine like terms. So 2x squared minus 5x, take away 18. Now I'm solving, so there's different ways of solving: graphing, completing the square, factoring, quadratic formula, but they all need to be in standard form. The quadratic needs to be in standard form. So I'm going to subtract 24 to each side to get 0 on one side. Negative 18 minus 24 is negative 42. Because my a value is 2, the best approach is going to be by using quadratic formula. So a is 2, b is negative 5, c is negative 42. So every time you have an a value that is something other than 1, let's go with the quadratic formula. Okay, so a is 2, we're going to use quadratic formula. That quadratic formula that you need to have memorized: x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's substitute. X equals negative 5 plus or minus the square root of negative 5 squared minus 4 times 2 times negative 42 all over 2 times 2. So x equals 5 plus or minus the square root of 25 plus 336 all over 4. That's 5 plus or minus square root of 361 over 4. The square root of 361 is 19, so 5 plus or minus 19 over 4. And now we're going to separate into two problems, because now I do want to add 5 and 19. And I also want to subtract 19 from 5. So I'm going to separate into two problems. 24 divided by 4 is 6, so one of my solutions is 6. 5 take away 19 is negative 14 divided by 4. I can reduce that fraction. That's 7.5, which is negative 3.5. However, I would normally box in that as a solution, but we're talking about the area of a rectangle. Length nor width can be negative, so I'm going to leave that on my PowerPoint here, but I'm going to cross it off because length nor width can be negative. Number 14, determine the number and type of solutions for this quadratic. So, if we only need to determine how many solutions there are and whether they're real or imaginary, I don't actually have to find the solutions. And in that case then, I can use a discriminant. The discriminant will tell me how many and what type of solutions there are. So remember, if the discriminant equals 0, then there's only going to be one real solution. If the discriminant is a positive number, then there's going to be two real solutions. And if the discriminant is a negative number, there's going to be two imaginary solutions. Those are my three options. Well, A is 5, B is negative 4, C is positive 2. Substitute negative 4 squared minus 4 times 5 times 2. Negative 4 squared, that's 16. 4 times 5 is 20. 20 times 2 is 40. And 16 take away 40, that's negative 24. I ended up with a negative number as a discriminant. So if there's a negative discriminant, then there's going to be two imaginary solutions. Don't know what they are. I just know that there's going to be two imaginary solutions. Okay, problem 15. Solve using any method. We can graph, we can factor, we can complete the square, we can use square roots, or we can do quadratic formula. Since I'm noticing that A is 3, I'm going to go with the quadratic formula. But I need to get this in standard form, so I need to move the 25 over to the other side. So 3x squared minus 6x plus 25 equals 0. Now it's in standard form. A equals 3, B equals negative 6, C equals 25, and the quadratic formula is negative b plus or minus b squared minus 4ac all over 2a. I'm going to substitute. X equals negative 6 plus or minus the square root of negative 6 to the second power minus 4 times 3 times 25 all over 2 times 3. That's 6 plus or minus the square root of 36 minus 4 times 3 times 25 is 300 all over 6. 6 plus or minus the square root of negative 264 all over 6. I'm going to simplify the square root of negative 264. Since it's a negative, I know I'm going to have an imaginary answer. So I need to break down. I'll do it over here on the side over here. square root of negative 264. I'm thinking of two numbers that break down what makes 64. I want one of them to be a perfect square, so right now I'm using my calculator. I'm doing 264 divided by 16. That's not nice, so let's do 264 divided by 4. Okay, I'm getting 264 divided by 4 is 66, so I'm going to break this down as negative 4 times 66. Okay, the square root of 4 is 2. The square root of negative 4 is 2y. Okay, now I know 66 is an even number, so 66, let me see, is 2 times 33. How can I break down 33? I can't. It's a prime. Oh, wait, no, it's not. Let me break it down. I can do 3 times 11. Okay, but now these are all primes, and neither one of them is a perfect square, so 2i radical 66. So x equals 6 plus or minus 2i radical 66 over 6. And now I'm going to reduce. The only thing left to do is to reduce. So I'm looking in 3 different places. What number goes into all 3 of those? And that's 2. So it's going to be x equals 3 plus or minus I radical 66 over 3. These are my 2 solutions, and they are imaginary. So why did I choose this method? Why did I use quadratic formula? Well, if you look at the solutions that we got using quadratic formula, we got imaginary solutions. But the main reason I chose quadratic formula was because A was 3. So since A is 3, quadratic formula is the best method we can use. Number 16, graph the inequality. Well, for part A, this is a quadratic, the parent function x squared, but it's been reflected and shifted down, translated 3 units down. So the vertex is going to be at 0, negative 3, 0, negative 3. It's the same size as the parent function, but it's going to be opening downward. So 1, 1, 2, 4, and I believe we ran out of space, so I'm just going to draw there. Okay, now before I make the actual parabola, I need to go back because this is an inequality. I need to look at the symbol at the inequality. This is a less than, so I'm going to make it a dashed parabola. Because it's less than, I'm going to draw an arrow from the vertex going down. This arrow's on the inside of the parabola, so I'm going to shade entirely inside. So all of these points that are in the shaded region are solutions to this inequality. Points that are on the boundary are not solutions because this is a dashed parabola. Okay, problem B. This is a parabola who's been shifted up 1 unit and who's been vertically stretched 2 units. So there's a vertical stretch of 2 and it's been shifted 1 unit up. So the vertex of this parabola is at 0, 1. Now, when I make the next set of points on the parabola, I'm going to go 1 to the right and 2 units up. And if I had space, I would go 2 units to the right, 8 units up. But that would be off the coordinate plane, so I'm just going to draw this many points. I'm going to look at the inequality. This is a greater than or equal to, so I'm going to connect the points with the solid line. Greater than or equal to, I'm going to put my pen on the vertex, make an arrow going up, greater than. This arrow is inside of the parabola, so I'm shading completely inside of the parabola. All of these points inside the shader region are solutions to this inequality. Number 17, graph the system of inequalities. There are two quadratics, so I'm going to draw two parabolas and shade in different locations. So I'm going to use blue for the first parabola. I need a vertex. So for the blue parabola, so for y is less than x squared minus 4x plus 8, my a value is 1, b is negative 4, c is 8. To find the vertex, I need to do x equals negative b over 2a. That's negative 4 over 2 times 1. That's 4 over 2, which is 2. To find the y value, I'm going to substitute. So 2 to the second power minus 4 times 2 plus 8. That's 4 minus 8. Take away 8. That's negative 4. Sorry, this should have been a plus 8 here. Negative 4 plus 8, which is 4. So the vertex of this parabola is at 2, 4. That's in quadrant 1. A is 1, so it's the same size as a parent function. So I'm going to plot some more points using the pattern 1, 1, 2, 4, 3, 9. Now before I connect those points, I'm going to go back, look at the inequality. It's a less than. If it's a less than, it's going to be a dotted or a dashed parabola. Less than implies that I should be shading below the vertex. So this little arrow that I drew is pointing down. It happens to be outside of the parabola. So that means that I need to shade all outside of this parabola. All outside. Okay, now I'm going to switch colors and I'm going to work on the next parabola. Okay, so the next quadratic is y is greater than or equal to negative x squared plus 4x plus 2. A is negative 1, so this parabola is going to be reflected. B is 4, C is 2. To find the vertex, I need to do x equals negative b over 2a. That's negative 4 over 2 times negative 1. Negative 4 divided by negative 2 is 2. Substitute. Y equals negative 2 to the second power, but the negative is not squared, plus 4 times 2 plus 2. That's negative 4 plus 8 plus 2. That's negative 4 plus 2. That's positive 4 plus 2, which is 6. So the vertex of this parabola is at 2, 6. Okay, this parabola has been reflected. 1, 1, 2, 4, 3, 9. Okay, this time I'm going to go back. I'm noticing that this is a greater than or equal to, so this would be a solid parabola. Greater than or equal to means I'm going to draw an arrow going up. I'm going to shade outside of this parabola, and as I'm doing so, I'm looking for the overlapping regions where the blue and the green overlap, because I am then going to take my highlighter and highlight that region, because those points are the solution to this system. So it would be, there's actually a couple of little regions, or big regions actually. Okay, this one on the right, and this one right here on the left. So the shaded regions, those points that land in those shaded regions, are a solution to this system. So problem 18 says decide whether each point is a solution to number 17's system and explain. So the first point I'm looking at is a point 20. Oops. The point 20. Okay, the point 20 happens to be right here, and notice that that is not a solution to the system. So this would be a no. The point is not in the common shaded region. So it's not in the highlighted area. Okay, letter B, 06. 06. That would be right here. And that point is in the highlighted area. So I'm going to say yes. The point is in the common. Is in the common shaded region. It's in the highlighted area. And what about the point 42? The point 42. 42. Ooh, that's right here. It's actually on the boundary of my second quadratic, but that boundary happens to be solid, and if it's on the boundary of solid regions, then it is a solution. So this is a yes. The point is on a boundary, on a solid boundary. And therefore, it is a solution. So points that are on solid boundaries are a solution, but points that are on dotted or dashed boundaries are not. So one more time. So if I were to ask something like, what about the point 48? Is 48 a solution? Then the answer to that one would be no, because that one's on a dashed boundary. But if it's on a solid boundary, it would be yes.